Today we will be talking about the One-Way ANOVA. This is another compare means statistical method. The One-Way ANOVA is an extension of the independent sample t-test. If you are unsure about the independent sample t-test, make sure to review the video we already uploaded about this, so you have the knowledge before switch to the One-Way ANOVA. This test, the One-Way ANOVA, is used when the researcher is interested in whether the means from several, more than two independent groups differ. For example, if a researcher is interested in investigating whether four ethnic groups differ in their IQ scores, the One-Way ANOVA can be used. In the example that we are going to use today, we are interested to know how the happiness at the workplace from a sample of 40 teachers differ depending on their educational stage, the place where they work, they teach. So we have here kindergarten, primary, high school, and university. We will explain this, of course, in greater detail later. For now, I just want to give you like the broad definitions about the One-Way ANOVA, when to use it, why to use it, the assumptions, and so on and so forth. So it is really important that you remember that when you run a One-Way ANOVA in any post-hoc tests, you are trying to determine whether there are differences between the groups' means in the population. That is, the statistical significance of the test is referring to the group population's means and not the group sample's means. So to be even more specific, you are assuming the null hypothesis, which states that there are no differences in populations means between the groups. So you're trying to find evidence against this null hypothesis and accept the alternative hypothesis, which of course states that the differences between the group populations means really exist. Now, the One-Way ANOVA as a null hypothesis significance test tells you the differences between the groups mean, tells you if the differences between the groups mean are real, but does not tell you the size of the differences or the difference. This size is also called magnitude. So in order to deal with this limitation, an effect size can be calculated. Now, the requirements for you to run One-Way ANOVA are basically three. There must be only one independent variable. So, for example, ethnicity, in our example, educational stage, and so on and so forth. Secondly, there should be more than two labels for that independent variable. So if your independent variable is ethnicity, you should have, for example, Australian, American, Argentinian, Chinese, Spanish, and so on and so forth. More than two labels for that independent variable. In our case, we have as independent variable educational stage, and as I already showed to you, we have four levels. And finally, the final requirement for you to run a One-Way ANOVA is that there must be only one dependent variable. Now, about the assumptions, as always, there should be no outliers, the data should be normally distributed, and you should meet the homogeneity of variance. I'm going to explain this in greater detail later, and how you check if this final assumption about the homogeneity of variance is met or not, and how to deal in both cases. So in order for you to run the One-Way ANOVA, you just have to come to Analyze, hover over your mouse over Compare Means, and click on One-Way ANOVA. Now I'm just going to display variable names here only so it's shorter. So now what you have to do is take the happiness score to the dependent list and move the group, the educational state, to the box factor. Today we are not going to talk about the contrasts, so we will just leave that untouched. Now let's go to the options box, and we want to check the descriptive statistics. We want to check the homogeneity of variance test, so we can check if this assumption is met or not. We also want the Welsh One-Way ANOVA. I'm going to show you later why we check this. In short, this is checked in case this homogeneity of variance is not met, so we have information and know how to deal with this. And we want the means plot. As perhaps you already know, the plot is a graphical aid for you to see or to understand the values that are displayed in the descriptives or in other tables. So we can click on continue, go back to the One-Way ANOVA main box, and now let's click on post hoc. As I said before, since you want to know the size of the differences between the groups, you need the post hoc tests. So as you can see here, there are a lot of options with what some people might call funny or weird names, but of course these are the names of the people who invented these methods. And you can see there are two major parts on this window: when the equal variance are assumed and when they're not. So I'm not going to explain every single option here, just a couple for you to understand something about them. So the first one is the LSD test. So this was the original solution to the problem about not knowing the size of the difference, of the magnitude of the difference. This was developed by Fisher, and was meant to explore all possible pairwise comparisons of means comprising a factor using the equivalent of multiple t-test. So LSD stands for least significant difference. Another popular post hoc test is the Tukey's HSD, which was developed as a reaction to the LSD test. And several studies have shown that the procedure accurately maintains alpha levels at their intended values as long as the statistical model assumptions are met. So once again, your assumptions are that your data is normally distributed, has a homogeneity of variance, and you have no outliers, and there are independence. So this Tukey's test was designed for a situation with equal sample sizes per group, but still can be adapted to unequal sample sizes as well. And finally, the Schiff's test. This procedure is probably the most popular of all the post hoc procedures because it's the most flexible and the most conservative. Schiff's procedure corrects alpha levels for all pairwise or simple comparisons of means, but also for all complex comparisons of means as well. So complex comparisons involve contrast of more than two means at a time. This in the end means that this procedure is also the least statistically powerful. So bottom line, because all of this, Schiff's test is a very poor choice of all these procedures unless complex comparisons are being made. If you use a Schiff's test when you are not using complex analysis, is a waste of statistical power and is really likely to lead to type 2 errors. So if I'm assuming you already have the knowledge about type 1 and type 2 errors, but to summarize really quick, the type 2 errors is when you do not reject your null hypothesis, when in fact the alternate hypothesis is true. But again, if you are unsure about this, you just have to consult your statistics book or books. I will also add some information and links at the post on the blog so you can read more about this. So that being said, in this post hoc window, we are going to select the Tukey on the equal variance assumed part. And one thing, you can select all of them if you want, but we're just going to select Tukey, and in the equals variance not assumed, we're going to check the game's Howell procedure. Why we're doing this? Because we don't know if our homogeneity of variance is met. So we need these two information. If our Levene's test shows that is the homogeneity of variance is met, then we can use the information from the Tukey. If not, we can use the game's Howell and also the Welch information. And the significance level is by default set at 0.05. If you want, you can be more strict and change it to 0.01, but for now we will just leave it as default. Click on continue. Click on paste so you can see the syntax behind the action you are performing. Select all these and click on run. So we have now the results of our one-way ANOVA procedure, and as you can see here, as usual, the information is divided in tables. We have the descriptive statistics, the test of homogeneity of variances, the actual scores or results from the ANOVA, the Welch, one-way ANOVA, the multiple comparisons, and the means plots. So we are going to analyze one by one. So of course the descriptives is just telling you about the population, how many participants are in the study, how many teachers in kindergarten, how many in primary, high school, university, and of course the total, the mean, the standard deviation, standard error, in all this basic information. Now let's move now to the test of homogeneity of variances, and we are interested now in the significance value. So with the Levene's test, if we have a p-value smaller than 0.05, then we do not have equal variances, and we have violated the assumption of homogeneity of variances. So as you can see here, we have a value of 0.09. So this assumption is met. Okay, this means that in this case we can disregard this information, this table of the robust test of equality of means. This is used when the significance value of your Levene's test shows a value smaller than 0.05. In addition, when you have not met the assumption of homogeneity of variances, you also need to read the information from the Games-Howell Posthoc test. But since we met the assumption in this example, we're going to use the information from the Tukey Posthoc test for our multiple comparisons. So now we are going to take a look at this table, the ANOVA table, and we want to take a look at this value, the p-value of the ANOVA. Since we have a value smaller than 0.05, this means that the results are significant. This means that there is a significant differences among the different educational stages in the group variable. So now when you are going to report this information in your article or homework you're doing for your statistics course, you can write it like this. So as you can see here, you are taking the F, the degrees of freedom from the between groups, which is 3, comma 36, the degrees of freedom from the within groups, that equals 69.5, which is the F value, and as I already said, we have a significance value smaller than 0.005. So let's close this and let's move to the next table. As I said before, we are going to focus on the 2K HSD since we made the assumption of homogeneity of variance. There are some duplicates here, so you see that we have this comparison kindergarten and primary, and we have also here primary and kindergarten. So we have to focus only on one in these cases where there are duplicates. So now once again, as in many statistical methods, you have to focus on the significance value, and as you can see here, all of them are significant. So we have a statistically significant difference between the educational stages and the happiness score of the teachers between kindergarten and primary, high school, university, and so on and so forth. Now we can for now disregard this table and take a look at this, the mean plot. As you see, it's a really useful graphical aid for you to see how different the happiness level varies across the educational stage. So in kindergarten, people is fairly happy. In primary, the happiness decreases. High school, the teachers are really unhappy. And at the university, once again, teachers are happy. So as I said before, probably you'll have to report the effect size of these ANOVA results, and in this case it's better to use something that's called the omega squared value. So this omega square is an estimate of the dependent variance accounted for by the independent variable in the population for a fixed effects model. So let me show you quickly the formula. Basically what you are doing is taking first the sum of squares of the in-between groups, then you have to rest the degrees of freedom times the mean square of the within groups, and that you have to divide it by the total information of the sum of squares plus the mean square of the within groups, and that will give you the coins D. So I'm not going to perform this on the video. This is something that I would like you to do as if you want, as a small homework for you, so you can calculate the effect size by yourself. And additionally, for this homework, you'll have to check if the value you have is small, medium, or large, and then you'll have the opportunity to perform something else rather than just see what I do on the screen. And with this we can conclude this video, and I'll see you next time. Thank you very much for watching and have a great day.